Okay, well, I think we're going to give this a shot, do this a little bit differently. We've got a little more time left today, and we finished chapter 12, and so I want to go ahead and get into chapter 13, which is now across the bridge that I talked about yesterday. The bridge being chapter 12 that just brings us from our intensive study of cycles that we've focused on so far. Now we're going to begin to look at modifications of our first law analysis to apply to mixtures, and in particular mixtures of ideal gases. And that's where we're starting in chapter 13. The first things that we want to talk about there are then how do we talk about the composition of a mixture. Well, we can either talk about the mole fraction or molar fraction I think the text uses capital N, and I often use a lowercase n to represent that. Divided by, yes, make that a little more plain. Okay, so what does this mean? If each constituent of a mixture is considered, I equals 1 to the total number, then the fraction of each component that's available is the total number of moles for that constituent divided by the total number of moles for the mixture. So the total number of moles for all, so that means we're going to add up all of the ones. He doesn't say in the book in terms of the notation, and I'll just say we have M components in the mixture. So if we add all of those up, the total number of moles, that gives us NM. So that fraction, we call that the molar fraction, mole fraction. Another way that we can talk about the composition, and it's equivalent, we can talk in a different way, is in terms of mass fraction. So mole fraction is one thing we can do, but we can also talk about the mass fraction. And it has the same kind of definition that you might imagine, but instead of the number of moles, we're talking about the mass of each constituent. And that notation is a little awkward right there. But to be consistent, the subscript M refers to the mixture, and the subscript I refers to an individual component. So this becomes our mass fraction, and we don't have a good shorthand for that, so we call that MF, mass fraction of component I, where Mi is the mass. And then M sub M is the mass, total mass of our mixture. Okay, so we can either talk about the mole fraction or the mass fraction. And likewise, of course, the total mass is just the sum of the mass of all of the individual ones. We just add them all up. That gives us the total mass. Now, you probably remember this is actually independent of ideal gases, but for any compound, the relationship between the moles and the mass is the molar mass. And my window's kind of small here. I have to keep remembering to move down. Recall that the molar mass, M, relates moles and mass. So the molar mass is in fact the number of moles, the mass per number of moles. And I guess we can write it that way to be a little more consistent. And so one of the things you need to be able to do with these is to switch back and forth, or to convert. If you have mass fractions and you need mole fractions, that you can find the one that you don't have, to convert back and forth between mass fraction and mole fraction. So how do we do that? I don't know. Let's take maybe kind of a simple example to look at this. That if we know the mole fractions, how do we find the mass fractions? So let's see if I can lead us through that. Okay, so let's suppose that we have, I don't know what, 3 moles of carbon dioxide, 5 moles of oxygen, 2 moles of water vapor. And I don't know if you want to throw something else in there or not. Maybe that's enough. But what are the molar masses for these? I'll put molar mass for CO2. If you look it up in the table, they'll give it to you very precisely, but very approximately, each oxygen is 16. So 16 times 2 is 32, and each carbon is 12. So the molar mass of CO2 is about 44. We write kilograms per kilogram mole. And likewise, for oxygen, I just gave that one away. We'll call that 32. And for the water vapor, 16 plus 2 times 1, we'll call it 18. Okie dokie. So if this is what we've got, then if we sum these up, that's going to be our number of moles of the mixture. 5 plus 2 is 7 plus 3 is 10. So that makes it nice. Then we can write down that the Y for the mole fraction for the carbon dioxide is just the number of moles of carbon dioxide, which is 3, divided by the total number of moles, which is 10, or 0.3, or 30%. And likewise, Y for the oxygen is 5 out of 10, and that's half of it. And for the water vapor, 2 out of 10 is 0.2. And of course, when we add those up, since these are fractions, they better add up to 100%. So that's just kind of a check. So if we've been given this information that these were the mole fractions, and then someone asked the question, what are the mass fractions? Then how would we do that? Well, what we have to do is start out and just assume that we have some convenient number of total mass that's present. And then based on that and the mole fractions, we can calculate how much is available in each group, or we can assume that we have the number of moles present. So let's start out with sure, for every 1 mole of mixture, then we want to find the mass of each constituent or component, and then add the total of that, and then find the mass fraction for each one of those. Okay, and this can be done pretty simply by maybe making a little table. So if we put the constituent CO2, O2, H2O, and then for each one of those, then let's put the given mole fraction. So we've got that 30%, 50%, 20%, and then I mean, let's put Ni. This is based on 1 mole, so this is kind of silly, but so now for each one of these we need to find out, that's the the molar mass, and we wrote those down up here before. This one's 44, this one's 32, and this one's 18. Now for each one of these we want to find out how much mass is present. How much is the Mi based on this Ni and the known 44. So since the mole fraction is the mass per number of moles, we need to multiply the number of moles times the mass fraction, the molar mass, and that'll give us the mass. Now this won't be the mass fraction, but that will be the mass of that many moles of carbon dioxide, and then we'll find the mass for each one and add them all up. So I'm going to try to do that because I don't have a terribly effective calculator, but I can maybe make this simple math work. 44 times 0.3 is 13.2 kilograms. And then 32 times 0.5, I can probably do that in my head. That's about 16. And then 0.2 times 18 is 3.6. And now I want to add all those up. So add these together. 32.8. And now for each one of those I want to find the corresponding MFI. How am I going to do that? The mass fraction is just going to be the mass of the individual component divided by this total. So 13.2 divided by 32.8 is about 40%. I'm going to call it 40.2. Alright, 4024. Maybe that's more digits than we can justify. Likewise, we've got 16 divided by the 32.8 is 48.78. And then the water vapor, which wasn't much at all, 3.6 divided by 32.8, 0.1098. And again, these are fractions, and so these should sum to 1, and that's a good double check. It looks like it's going to be close, but I don't think I'm going to get there because this doesn't end in a 0. Oh, yeah, it does. So take 2 over here, yeah. So I think it works out. Yep, the sum is 1. So obviously if you were given the mass fractions and you needed to work back to find the mole fractions, it's the same procedure. You would just build this table from the right to the left. So, I mean, you would put mass fractions here, assume 1 kilogram or 10 kilograms, whatever you wanted to assume for the number of kilograms present for each constituent, then calculate how many moles there are, find the total number of moles, and then find the mole fractions. So you could go from one to the other or back and forth that way. We might need to know the average molar mass for this mixture, if you will. And how can we do that? The average molar mass for the mixture is the mass for the mixture divided by the number of moles for the mixture. And we can generate that from our simple analysis here, because we assumed that we had 1 mole total and these added up to 1, then we just need to find this total mass divided by this total number of moles, and that's going to give us the apparent molar mass for the mixture. And I'm writing the units here as kilograms per kilomole of mixture to maybe emphasize that. And then I don't know, sometimes it comes up if we're talking about ideal gases and we need to know the gas specific constant. We'll take the universal gas constant, and divide it by divide it by the molar mass. And so we could do that here. And if we're talking about ideal gases, let's review a little bit of ideal gas law behavior, ideal gas behavior. I don't know if you recall back from your physics, but there were some talk about the Dalton model and the Amagot model. Let's just first write down the equation of state for ideal gases. This is for a particular gas. When we talk about the components, the mixture of gases, it's pretty easy to say that when we have a mixture of gases, that they all are at the same temperature. If it's a homogeneous mixture, if it's been, it's at equilibrium, that the temperature's all the same. But it's not so obvious if we talk about the pressures and the volumes. They can't both simultaneously be the same. Why is that? Well, if we think about two gases occupying a space, and if we assume that they both occupy the entire space, which seems reasonable, then they would have to each have a pressure, a partial pressure, a pressure less than the total pressure, so that they added up to the total pressure. And this is the Dalton model. I'll write it first. I guess I'll be explicit here. Dalton model for mixtures of ideal gases says that all constituents or components are at the same temperature and occupy the entire volume. But each constituent or component exerts a component pressure, partial pressure, so that the total pressure for the mixture is the sum of these partial pressures for the mixture. Okay, so that's the Dalton model, and that's actually the one that we're going to work with the most. An equivalent view has been formulated by Amagot in Amagot's model. Amagot model says that everything is at the same temperature and pressure, and that each gas occupies only part of the volume. So that the volume total is the sum of the individual volumes. Okay, and well, the really interesting thing about this is that it turns out that no matter which of these models you follow, it turns out that the pressure relative to the mixture pressure, component pressure relative to the mixture pressure, is equal to the component volume relative to the mixture volume, and that's the same as the number of moles. Oops. In other words, this mole fraction ends up being very important to relate to help us find these partial pressures, the PIs. If we know the total pressure and we need to know the partial pressure, if we know the composition of the gas, that's all we need to know, and then we can find it. So this mole fraction that we were just talking about earlier becomes an important piece of information for us in analyzing a mixture of ideal gases. Okay, well, I'm not real sure how much time we have left, and I don't know if it's useful to work another example similar to this one that we did about finding the gas compositions. But I'm going to maybe just end it here for today. But to maybe remind you that there's a test on Tuesday, and you can bring a reference sheet of notes. And what else do I need to tell you? That you can expect probably, what did we say? We're dealing with everything from the Brayton cycle through refrigeration. And so we talked about Brayton cycle, and we talked about regenerator effectiveness for Brayton cycle. And we talked about refrigeration cycles, and we talked about simple refrigeration cycles, but we also talked about some different advanced or modified refrigeration cycles. We had the cascade cycle, we had the two-stage compression cycle. I worked out an example at the beginning of class today using Excel. So all of those are fair game, and I think you can expect maybe one problem out of each of these categories, right? That's what you can expect on a test for Tuesday. So I will be able to respond to email. So if you have questions that come up either on that homework that I assigned you or about other things, feel free to email me. As I say, I may be tied up during the day on Monday, but may be able to I will be able to get back to you in the evening for sure. Okay, well, that's it. Thanks for your attention, and have a great day.